Before 1865, electrical phenomena and magnetic phenomena were treated as distinct physical forces. James Clerk Maxwell fundamentally changed physics by synthesizing the work of Coulomb, Gauss, Ampere, and Faraday into four coupled partial differential equations. These equations describe how electric fields, E, and magnetic fields, B, are intrinsically linked components of a single electromagnetic field. They precisely define how charges and currents generate fields and, critically, how changes in one field generate the other. The differential form relates field properties at a specific point in space, which is essential for microelectronic simulation and finite element field solvers. The integral form relates fields over defined surfaces and volumes, proving useful for macroscopic circuit analysis and solving boundary condition problems. Maxwell's formulation demonstrated that E and B fields are inseparable. Gauss's law for electricity defines the precise relationship between static electric charge and the electric field it produces. The electric flux passing through any arbitrary closed surface is directly proportional to the total electric charge enclosed within that volume. Mathematically, the divergence of the electric field, E, equals the charge density, ρ, divided by the permeability of free space, epsilon naught. This law explains the operation of parallel plate capacitors, where charge separation creates a uniform electric field between the conductive plates. In semiconductor physics, this principle governs the width of the depletion region in p-n junctions. Fixed donor and acceptor ions within this region create the internal electric field barrier necessary for diode rectification and transistor operation. Gauss's law for magnetism states that the net magnetic flux passing through any closed surface is always identically zero. This physical constraint implies that magnetic field lines are continuous loops. They possess no starting points and no ending points. Consequently, the divergence of the magnetic field, B, is zero everywhere in space. This law confirms the non-existence of isolated magnetic charges, known as magnetic monopoles. All magnetic sources must exist as dipoles, whether generated by permanent magnets or by current loops. This constraint is fundamental to designing efficient inductors and transformers, ensuring that the magnetic flux closes entirely within the high permeability core material to maximize coupling efficiency and minimize detrimental leakage flux. Faraday's law of induction describes the mechanism by which a time-varying magnetic field generates a circulating electric field. The electromotive force, EMF, induced in a closed conducting loop is precisely equal to the negative rate of change of the magnetic flux passing through that loop. In differential form, the curl of the electric field, E, is equal to the negative time derivative of the magnetic field, B. This principle is the essential basis for all electrical power generation systems, including alternating current generators and dynamos, converting mechanical rotational energy into usable electrical energy. In electronics, it governs transformer operation, enabling efficient voltage step-up or step-down, and dictates the back electromotive force generated in motors and inductors, which inherently opposes any change in current flow. Ampere's circuital law relates the magnetic field circulating around a closed loop to the electric current passing through the enclosed area. Specifically, the line integral of the magnetic field, B, around a closed path is proportional to the enclosed conduction current. This law explains how steady currents, such as direct current flowing through a transmission wire, generate a surrounding static magnetic field. This relationship is critical for designing powerful electromagnets, solenoids, and calculating the magnetic coupling between adjacent traces on a printed circuit board. However, Ampere's original formulation was incomplete when dealing with time-varying fields, failing to conserve charge in non-steady-state situations such as the charging cycle of a capacitor. Maxwell introduced the concept of displacement current to resolve the critical inconsistency in Ampere's law under non-steady-state conditions. Displacement current is not a flow of charge, but rather a term proportional to the rate of change of the electric flux density. By adding this term, Maxwell ensured the fundamental principle of charge conservation and established perfect symmetry between the electric and magnetic field equations. The complete Ampere-Maxwell law states that the curl of the magnetic field is generated by both the conventional conduction current and the newly defined displacement current. This correction is essential for understanding all high-frequency phenomena where the displacement current dominates over conduction current, particularly within dielectric materials and insulators, enabling the propagation of electromagnetic waves through empty space. The inclusion of the displacement current term allowed Maxwell to mathematically combine the four fundamental equations into a unified wave equation. This powerful equation predicted the existence of self-propagating electromagnetic waves. In these waves, an oscillating electric field generates a corresponding oscillating magnetic field and vice versa, sustaining propagation without a medium. Crucially, the calculated speed of these waves, derived solely from the permeativity and permeability constants of free space, exactly matched the known speed of light. This established the profound realization that light itself is an electromagnetic wave. This unified theory underpins all modern wireless communication, including radio frequency, microwave, and optical systems, and dictates the fundamental limits of antenna and waveguide design. Maxwell's equations are the absolute foundation for analyzing signal integrity in all high-speed digital circuits. Transmission line theory, which governs impedance matching and the minimization of signal reflections on printed circuit boards, is a direct mathematical consequence of the electromagnetic wave equation. In microelectronics design, advanced electromagnetic simulation tools utilize these equations to accurately model complex phenomena such as crosstalk between adjacent traces, noise propagation within power delivery networks, and the radiation patterns of integrated antennas. The precise behavior of all radio frequency components, including filters, resonators, and couplers, is entirely derived from applying the boundary conditions imposed by the four fundamental laws onto conductors and dielectric materials at high operating frequencies.